Hello and welcome back to another episode of the natural number game using Lean 4. Today we'll be attempting the power world. So, quick recap, before we did the addition world, proved a bunch of theorems, multiplication world, proved a bunch of theorems. Today we'll be tackling the power world. To start, we're going to need to define the power function and prove some things about it. So similar to the add function and the multiplication function we're going to start by defining a new function for exponentiation on our natural numbers. Define pow, mn, both mynats, and this returns a mynat. And how do we define it? Well, we can match n with a few different cases. If it's a 0, well then anything to the power of 0 is 1, and its successor of n prime, well, okay, let's think what that is. M to the power of n prime plus 1, well, that's equal to m to the power, not times m to the power, that's equal to m times m to the power of n prime. So that is how we're going to define it, and then we can also just, so successor of n prime, well, we'll have, I guess we just use the mole function, mole m times what? Well, pow m n prime. Okay, now let's do some examples. Pow 1 to the power of 0 will be equal to 0, or equal to 1 by Ruffle. Example, did that work? Yes. Example, pow, let's see, 2 to the power of 3 should be 8. And pow 3 to the power of 2 should be 9. Raffle. Okay, what about 0 to the power of something? All example, pow 0 to the power of 2 should be 0. Ruffle, and 0 to the power of 0, the way we've defined it, since the second thing is 0, it'll be 1. 0, 0, 1. Ruffle. That's just because, well, that's how we define it, and it's useful in math to have 0 to the power of 0 be 1. Great, and then similarly, we want to be able to use exponentiation. So right now, if I try to do 0, or I guess just 0 to the power of 0, well, it says doesn't know what power is for a natural number. So let's add an instance. Instance pow mynat, where pow equals pow. Oops, pow is defined as pow. Is that how we do it? Is it maybe not called pow? Okay, that looks right. What did I do wrong here? Instance pow. Okay. Pow defined as pow. Let me try to figure out what went wrong here. After some research, as I'll figure out what went wrong, I need to have 2 mynats here, because the reason is, unlike multiplication or addition, where only one type is required. For power, the second thing can be not this, like the second parameter passed in the power function could be a different type than the first thing. So like a natural to the power of a fraction, or like a real number to the power of a natural. So in that case, since we're just dealing with natural numbers, we want to be pow minat, and then everything works fine. And then now this example should work. Yes. Oops. And then this can just be able to say 1. Great. Okay. Now we have our pow function. Let us add a couple of axioms, and then we can do that in the power world. So our first axiom will be pow 0, where a is minat, and we're going to say that, well, a to the power of 0 is equal to 1, and that is reflexive. And let's make sure to import minat and open minat. That worked fine. Nice. Minat. Cool. And then similarly, we can do lemma pow successor a minat, where we're just going to say, well, a to the power of successor of b is equal to, what do we write that to be equal to? We said that's equal to m times pow again. Okay, I can just copy this over and then change the relevant variables. A times a to the power of b, and just like you saw with my copy paste, that's just true reflexively. And now let's jump into some more lemmas. Okay, first one, lemma pow, lemma 0 power 0, where we have 0 minat to the power of 0 equal to 1. And just make sure these are all natural numbers. Nice, okay, I just need to, because I think if I have it like this, it might not know that these are natural. Yeah, we're using my natural numbers, not the built-in ones. Okay. And can we do this reflexively? Yes. Okay, well, that's easy. Just because anything in the power of 0 is 1. Cool. Now let's lemma 0 power successor. And that's for m minat. Oops. We want 0 to the power of successor of m to be equal to 0. Okay, this is a little trickier, because we can't just use a reflection because, well, we don't, it's not definitionally equivalent that 0 to the power of something is that. This ends up being 0 times 0 times 0 times 0 successor m times. So we have this repeated thing going on. I'm probably going to use induction. We're probably going in, and there's only one variable to induct on. Induction m with 0 successor m prime inductive hypothesis. Okay. Well, we have 0 to the power of successor 0. Well, we can rewrite successor of 0 as 1. I think we did a multiplication world. For the addition world, where do we have 1 equals successor 0? Okay. Let's make sure to copy that over and import mynat.addition world. Okay. Now we have, did that work? Oh, I think we need to do it in reverse. Okay, and now we can apply our 0 pow 0 lemma. Nice, and now we have 0 to the power of 0. Did that work? Oh wait, what happened here? Well, I have 0 to the power of 1. Let me think. Okay, after thinking about this a bit more, I realized that we don't have a way to prove this is equal to 0 from what I know. If you have an idea in the comments, let me know. But what we do have is the power successor function, which we can apply before we change the suc 0 to 1. So if we apply power successor here, we have 0 times 0 to the power of 0, and then now we can apply mul 0 from our multiplication world. Multiplication world. A times 0 equals 0, or 0 mole, I guess. Okay, since all of these I forgot are written in terms of the word 0 are not the numeral 0, I'm just going to change these to be like this. Okay, that work? Nice, now 0 equals 0, reflexive. Okay, in this case, what do we have? 0 to the power of successor of m prime. Here we can do the same, rewrite power of successor, 0 mole, reflexive. And now I realize, since I didn't actually use the inductive hypothesis at all, I don't probably need induction. I think it'll just work in the general case, because we're going to be multiplying by 0 on the left, and then we could use 0 mole. Cool. Let's move on. Pow 1 lemma pow 1 a mynat a to the power of 1 is equal to a. By what? A to the power of 1 okay, I think we just apply pow successor pow 0, but let's first rewrite 1 as successor of 0. Okay, so we turn to that. We apply pow successor. A times a to the 0, and then a to the 0 is 1. So we have a times 1, and we can apply mul 1. And then we can be done. Heck yeah. Pow add, lemma pow add for a, m, n, all my naturals. A to the power of m plus n is equal to a to the power of m times a to the power of n. This is like the distributive law for power, like how you can distribute this m plus n over a to the power of that. Cool, and this is how you kind of turn addition to multiplication through the power of exponentiation. So let's think how to do this. So we have pow 1, we have 0, pow successor, pow 0. I'm guessing I don't see a direct way to do this. We might need to use induction for this one. M plus n, m plus n. Or I guess we could turn m plus n into successor m plus, or no. Not too sure about this. Let's see. It'd probably be induction on A or induction on M. Let's see what induction on A gets us. Successor A prime. So we have successor of A to the power. Well, we don't really have anything in our tool belt for successor of a to the power of something, so I'm guessing it's not induction on a, it's induction on m. Okay, so here we have a to the power of m prime plus n is equal to that. Okay, this is already looking promising. I think if we just like pull a successor of, like, if we pull this successor out and have that be a times m prime plus n, that just matches this. Let's pull out the successor. Can we apply pow successor? Does this work? Okay, so before pow successor we had this, after we have, yeah. Okay, we applied pow successor to the bottom one. Kind of want to apply to the left part of the equals. Let's apply another pow successor. This didn't work because the successor of m plus n, not successor of m plus n, so we wanted to do probably something in our addition world we can use. Successor add. And now we can use pow successor again. Okay, now we can apply our inductive hypothesis. And now we can multiplication is associative. And now we're done. Oh, and then we have to take care of the 0 case, obviously. A to the power of 0 plus n. 0 plus n is just n, so we write 0 add a to the power of 0 is 1 pow 0, 1 mole, and careful. Cool, that's power add done. And I'll save the rest of the power world for the next video. Thanks so much for watching. In the next video, we'll work on mole power, power to the power, and add squared. Add squared is a cool one. Like the final boss of this world is going to be things of a plus b squared. To prove that is equal to a squared plus b squared plus 2ab. So you can look forward to us trying to solve that in the next video. But yeah, thanks so much for watching, and leave a like and a comment if you found this interesting.